Hi, my name is Kimberly Chan and I'll be presenting our work on echo time optimization for J-difference editing of glutathione at 3T, which was recently published in Magnetic Resonance in Medicine. Glutathione is the brain's main antioxidant, and glutathione abnormalities have been implicated in the pathophysiology of several neurological disorders. Spectral editing is often used to detect glutathione in vivo. However, it is difficult to estimate the optimal echo time for J-difference editing of glutathione due to strong coupling and T2 relaxation effects. As a result, a large range of echo times from 68 milliseconds to 131 milliseconds has been reported as optimal for in vivo J-difference editing of glutathione. The aim of this study was to investigate the echo time-dependent modulation of edited glutathione signals to determine the optimal echo time for detecting glutathione. In J-difference editing of glutathione with megapress, there are two sub-acquisitions: an edit on acquisition where the editing pulses are applied to the glutathione signals at 4.56 ppm, and an edit off acquisition where the editing pulses are placed off resonance. Subtracting the off acquisition from the on acquisition results in a different spectrum, which contains the edited glutathione signal at 2.95 ppm. We examined the echo time modulation of glutathione with both simulations and phantom experiments and verified this in vivo. All simulations were done at a Benioff field of 3T with 20 millisecond editing pulses. The simulations were spatially resolved in the two directions defined by slice-selective refocusing pulses. Echo times from 70 milliseconds to 240 milliseconds was simulated, with two types of refocusing pulses: the vendor standard amplitude-modulated refocusing pulses with a bandwidth of 1300 Hz, and frequency-modulated refocusing pulses with a bandwidth of 2200 Hz. Matched experiments were performed in a 50 millimolar glutathione phantom on a Philips 3T Achieva scanner. The in vivo signal curve was then estimated from the phantom data. T2 relaxation in the phantom was removed and replaced by a term representing in vivo relaxation. We assumed in vivo T2 limits of 67 milliseconds and 89 milliseconds, and assuming a phantom T2 relaxation of 260 milliseconds based on the similar GABA phantom. In vivo experiments were done in 5 healthy adults in the 3.6 centimeters cubic parietal region of the brain at echo time 68 milliseconds, which is commonly used, and 120 milliseconds, which was determined to be optimal from simulations and phantom experiments. The long TE experiments was performed with the refocusing pulses simulated earlier. Gannett was used for frequency and phase correction of the spectra to the NAA peak, and then the GSH peak at 2.95 ppm was integrated with CSX3. Here are the results of the spatial simulations of the glutathione peak at 2.95 ppm. It can be seen here that there are two different regions within the voxel: a green region where the coupling behaves as intended, and a red region where it does not. As you can see in the off spectra, the multiplets are negative as desired in the green region, but are positive in the red region. On multiplets were positive as expected in all regions. The difference between the two, labeled diff, results in a positive signal in the green region and no signal in the red region. This amounts to a signal loss of 16% when refocusing pulses with a bandwidth of 1300 Hz were used, and a signal loss of 9% when refocusing pulses with a bandwidth of 2200 Hz were used. Adding up the spectra within the voxel and plotting the multiplet as a function of echo time results in the multiplet with the maximum amplitude and integral at 160 milliseconds to 170 milliseconds. Results from matched phantom experiments are in good agreement with the simulations in both the shape of the multiplets and on, off, and diff integral curves. Looking at the signals as a function of echo time, we can see that the maximum signal occurs at an echo time of 160 milliseconds if T2 relaxation is not considered. Accounting for in vivo T2 relaxation, however, this moves the echo time at which the maximum signal occurs to 120 milliseconds. In vivo, it can be seen that the glutathione peak is 57% larger when higher bandwidth refocusing pulses are used. In addition, editing at an echo time of 120 milliseconds results in a 15% larger signal than an echo time of 68 milliseconds. Simulations and phantom experiments indicate that editing at an echo time of 120 milliseconds in vivo yields a higher glutathione signal than at an echo time of 68 milliseconds. This higher SNR at an echo time of 120 milliseconds than at 68 milliseconds was also verified in vivo. However, this increase is less than the predicted increased benefit of 42 to 55%. This could be due to a number of reasons. The in vivo T2 relaxation being less than 67 milliseconds are due to the fact that GSH multiplets at the shorter echo time have negative outer lobes, which leads to the misidentification of the baseline in vivo. A further benefit of the longer echo time is that it allows for the use of improved slice-selective refocusing pulses. The majority of this signal increase is due to the improved slice profile of these refocusing pulses. A secondary benefit is due to the reduced chemical shift displacement artifact from the higher bandwidth of the pulses. To conclude, I'd like to acknowledge our funding, and for more information you can check out our paper which was recently published in Magnetic Resonance in Medicine.